So I'm Ken Delaney. I'm the industry liaison for the FREEDM Systems Center. We are the Power Electronics and Power Systems Research Center here at North Carolina State University. We have a dozen faculty, over 100 graduate students, and about $6 million a year in research funding from federal agencies, corporate sponsors, and state level projects. We have multiple labs, including our high bay, where we conduct high power testing at up to 15 kV. These are our research pillars, which explains a little bit about what the work that we do in wide bandgap power electronics, electric transportation, modern power systems, and renewable energy. Our industry members engage with the center in multiple ways, including leveraging research funding as project partners, early access to intellectual property, discounts on testing services in our labs, attendance at our annual conference, and of course, interactions with our students. Today's speaker is Srivatsal Sharma, a postdoctoral research scholar here at FREEDM. He received his PhD in electrical engineering from NC State in January 2024, an MS in electrical engineering from the University of Minnesota in 2012, and his bachelor's from the National Institute of Technology, Tiruchirappalli, India in 2011. Prior to joining the PhD program, he was a research engineer in the electric drives department at the Research and Innovation Center for Ford Motor Company, and a technical lead in the Energy Systems Department at Mahindra Electric Mobility. His research interests include DC microgrids, energy systems, transportation electrification, renewable energy, and wide bandgap devices. Sure, that's all. Come on. No. Yeah. Speaker should be on.
Yeah, hello everyone, and thanks Ken for the introduction. So the topic of today's webinar is control of power electronic converters for DC microgrids. And this is a brief outline for today's talk. I'll start with a brief introduction to microgrids, and then I'll give a brief overview of control methodologies, highlighting some of the limitations of the state-of-the-art technologies. And then I'll try to go deep into one of the proposed control methodology, and I'll try to end the seminar with a summary of the stuff that we will discuss. So what is a microgrid? Microgrid is a group of loads and distributed energy resources connected together. And microgrid could be in the form of an AC microgrid or a DC microgrid. Depending on whether we are forming an AC bus or the DC bus, the number of power electronic converters and the type of power electronic converters that would interface these distributed energy resources to the bus will be different. The figure on the left shows us an AC microgrid schematic, where I'm integrating wind turbine energy storage system, DC loads, AC loads to the bus. And similarly, figure on the right shows us a DC microgrid. And these figures show that the type of the converters and the number of converters would differ if we are forming an AC microgrid or a DC microgrid. Now let's look at some of the vision for the microgrids. So there has been an increased popularity in the deployment of microgrids, and some of the reasons for that are: a microgrid enables a more resilient and reliable system, especially in black sky events. Microgrids support more decarbonized electricity infrastructure by deploying energy storage systems, PVs, to form the microgrid system. And the third, and I think one of the most important, is that it supports an equitable energy transition by supplying electricity in rural areas where the presence of grid is still sparse. So with all these visions, the importance of microgrid has kept on increasing in the recent years. Now, I just described two configurations of the microgrid. One was an AC microgrid and other an DC microgrid. And here is a very small comparison between the two microgrid systems. So in comparison, my talk, both the microgrids are important, but this talk focuses more on the DC microgrid aspect. So I'm highlighting some of the advantages of DC microgrids. One of them is that it enables integration of photovoltaics, energy storage systems, and electric vehicles with fewer conversion stages. That means there is a less loss, and also the number of power electronic converters reduce. The other advantage of DC microgrid is that it enables simple control because there is an absence of reactive power and harmonics in the system. Some of the applications of DC microgrids are charging stations, data centers, more electric aircraft, marine applications, and emergency power sources. And in today's talk, I'll focus more on an application of emergency power source, which is being enabled by electric vehicles. So I'll try to go deep into mobile DC microgrids, highlighting some of the motivation for the mobile DC microgrids and their application. So like I just described, so one of the big vision of microgrids is that to support and sustain electricity during black sky events. And these mobile DC microgrids, as shown with an example here in the figure, they are enabled with mobile sources such as electric vehicle and energy storage systems. And in this particular example, they are being used to power a military camp at an army base. So for this particular application, they don't only help us in sustaining electricity during black sky events. At the same time, they are the main source of electricity for such an application. Now, apart from their use, these microgrids have significant economic advantages as well. And to highlight that, there has been a report presented for an application of microgrid at an army base, that when these microgrids are deployed at army bases, they help to contain the fuel saving. And for that particular application, since at an army base, there is a lot of fuel that is being transported at remote areas. So 55% of the army fuel consumption is just used to power the base camps. And along with that, since there are a lot of vehicles, army vehicles that are being used at the base camps, and most of these vehicles are being converted to electric vehicles, but these 90% of the time it has been shown that these vehicles are idle. So if we can use those vehicles to power the base camp itself, then it could help us to limit the amount of fuel that is being transported to these camps. And that has been shown that it can at least lead to 25% of the fuel saving, which is very significant because these base camps are located at remote areas, and there's a lot of cost associated with the transportation of fuel. Now let's go into a bit more technical aspects. So I'll present a brief overview of the control methodologies because we have multiple EVs and energy storage systems present in to form the microgrid. And when we parallel them, we want to ensure current and power sharing in a desired ratio among them. So for that, I'll present a brief overview of control methodologies first, and then go to one of the proposed control methodology. So just before I go to control methodologies, I will also like to highlight one of the important aspect of microgrid, which is the configurations in which the microgrid can be set up. So one of the figure on the left shows us the most simple configuration, which is a radial configuration, in which there is typically just a single bus formed, and all the energy resources are being connected through power electronic converters to form a single bus. So this is a very simple system, easy to deploy, but it has limitations that there is a single bus, so there is a single point of failure for radial configuration. To try to eliminate that limitation, we go towards a ring configuration in which there are multiple nodes. And as an example shown here in the middle figure, we have 4-node system where we have a military camp or any camp or at each node, and the source, which could be electric vehicle or energy storage systems. So this system helps us to improve the reliability because there is a redundant power flow, and thus it helps us to improve the reliability of the system. To further increase the reliability, we can go towards a mesh configuration. And as shown in the figure on the right, I'm connecting die nodes 2 and 4. So there is an additional tie line which is connecting 2 nodes, and that means that the reliability is further increased because at node 2 and at node 4 we have now 3 paths for the power to flow. So it helps going from radial to ring to mesh. We are increasing the reliability of the system. And the objective of this work is that all these systems are important for particular application. And so the control methodologies that are being studied and that we are trying to propose should be generic for all the microgrid configurations. Now going to the control methodology. So one of the control methodologies that is being actively studied in the literature is called as democratic current control strategy. And in that control strategy, with the figure on the left bottom, I'm trying to show how the converters can be modeled. So in this particular case, all the converters can be modeled as the current sources. And there is a central voltage controller which takes into account the bus voltage and generates a current reference for all the converters. So all the converters receive information from a central voltage controller, which are basically the reference current commands. Now, one of the limitation of this approach is that there is a lot of communication involved because all the current references have to be communicated to all the converters. But the advantage, and also another disadvantage, is that there is a central point of failure because the central voltage controller collapses and the entire system falls apart. But the advantage of this method is that it helps us to ensure a very regulated DC bus and also achieves accurate current sharing. To overcome the limitations of democratic control, there is a strategy called a leader-follower strategy, in which there is a leader, which is modeled as a voltage source. And so that leader basically takes into account the load voltage and generates a current reference for all the other followers. And the followers here can be modeled as the current sources. So as compared to democratic current strategy, this strategy has an advantage that there is a master controller, and the master controller feels then some other controller can be assigned a master controller. But at the same time, this strategy also involves a lot of communication, since the current references have to be communicated from the master or the leader controller to all the follower controllers. The third strategy is a group control. And this particular strategy, all the sources can be modeled as voltage sources along with their group resistance. Now, how do we form a group resistance? That we will see in the later slides. But the advantage of this approach is that there's no interdependence between the converters. Since all the converters are independent, it's easy to expand. And the other important advantage is the reliability. So since all the converters are modeled as voltage sources, if one converter fails, then the other can still continue to regulate the DC bus, and thus there's a high reliability and redundancy in the system with the group control. Considering these advantages, in this work, I'm focusing more on the group control and trying to understand how this group control strategy can be implemented for different microgrid configurations. Before going deep into the group control, I'll just highlight some of the basics of it. So in a group control with a conventional linear group system, we typically form a group characteristics. And in this particular case, figure on the top left shows us the group resistance, which is basically the slope of the variation of the reference voltage or the converter with the current. So we reduce the reference voltage of the converter as the current is increased to a point where the current limit of the maximum limit of the current of the converter is achieved. And also we would limit what is the minimum voltage that is allowed in the system, so which is being given here by VDC min. So with these characteristics being formed, we can define the group resistance, which is nothing but the slope of this line. Now let's take an example that how the group resistance, once we define the group resistance of a converter, how does it help us to achieve current sharing between the converters? So for that, I'll take a very simple example with two converters parallel together, with the group resistances RD1 and RD2, and the reference voltage of the grid is VDC star, and the current contribution for the two converters are IDC1 and IDC2 respectively. And in this simple system, they are feeding a load with impedance Z load. Now, if I solve the KVL equations, Kirchhoff voltage law equations for this particular system, I can show that that ideal current sharing between the two converters can be achieved in the ratio proportion to their group resistances. So once we define the group resistances, the converters will naturally try to contribute according to that, and we will achieve current sharing between the two converters. But now so this is an ideal system where we could achieve current sharing with the group control system. Now let's look at a practical system. In a practical system, along with the group resistance that we are defining, there would be certain cable resistances present in the system. So in this particular case, these cable resistances are the resistance of the cables using which the sources are connected to the DC bus. So for this particular example, I'm connecting source 1 with the cable resistance of R line 1 and source 2 with the cable resistance of R line 2. Now, what the presence of cable resistances does is fundamentally it modifies the group characteristics, which can be seen on the figure on the left. So initially we had the group resistance just at the slope of this black line. Now, due to the presence of cable resistance, the group curves change, and so that would modify the slope of this curve that the converters would see due to the addition of the cable resistance. Now, if I again solve the KVL equation for this particular system, we will achieve the current sharing is not only proportional to the group resistance, but also is a function of cable resistance. And thus we lose the accurate current sharing due to the presence of cable resistance in the system. So this is one of the very big limitation of the group control, which has been in existence for quite a long time, and people have studied it to eliminate that limitation. Now, one of the way to eliminate this limitation is we modify these group characteristics with certain offsets. So for ith converter, I can try to introduce an offset beta I, which shifts this curve slightly up or down depending on the loading conditions, and that would modify the group resistance. Now, how do we obtain this offset beta I? It could be done in multiple ways, and I'm classifying these methods in 3 categories. In approach 1, where we could, since we have a rough idea of the cable resistance that we are using, we know the cable length, and we can obtain the cable resistance, we use the estimates of those cable resistances to estimate beta I. In the second approach, we don't use the estimates of cable resistance, but we exchange some of the converter related information between the converters or the bus voltage information to all the converters to estimate beta I dynamically. And in the third approach, we don't limit ourselves to a linear group approach, which is shown here on the figure on the top left, but we could form a non-linear group where this function it's a non-linear function. The variation of the reference voltage with current is a non-linear function. So these are typically the three approaches that have been studied in the literature. And I'll just briefly compare the approaches in terms of performance, communication dependence, and prior estimate and the prior estimate of the cable resistance. So approach one, it does achieve accurate current sharing, which is our performance metric. It does not depend on communication, which is something really great, but it has a limitation that it uses prior estimates of the cable resistance. So we have to be very careful and accurate in terms of estimating the cable resistance. Approach 2 also has a good performance in terms of achieving accurate current sharing, but it has a limitation that it does depend on the communication. So basically, it counters the fundamental principle of group control that all the converters are independent. But due to the presence of communication, there is additional complexity that gets added with this approach. But it does not depend on the prior estimates of cable resistance. So it doesn't get affected due to the errors in the cable resistance. And the third approach is a nonlinear group approach. The good part of the nonlinear group approach is does not involve communication. It does not involve prior estimates of the cable resistance, but it is limited by the performance. It does not always guarantee accurate current sharing. Now, in our research, we have investigated all the three approaches, but in the interest of time in today's talk, I'll just focus on the approach one, where we use the estimates of the cable resistances. Okay, so what is the motivation for this particular approach? So one of the big motivation is that that especially for the applications where the microgrid is deployed in military areas, there is inertia to use the communication networks because they are vulnerable to cyber attacks. So that was the one big motivation in order to understand that why do we want to study the approach where we use the cable resistance. So like I said, this approach uses the prior estimates of the cable resistance. And this particular approach has also been studied quite extensively in the literature, but it has been limited to the radial configuration. And I'll just try to show what people have done in the literature in order to achieve accurate current sharing with this particular approach. For that, the figure on the left side is still the same, where I'm showing the loop resistance. Then I'm showing how the loop resistance gets affected due to the presence of cable resistance in red color. And then the beta I that we estimate for this particular method using the estimates of cable resistance, how it modifies the reference voltage of the converter that is being used. Figure on the right shows us the equivalent circuit for a radial configuration with n converters parallel together. So the loop resistance of all the converters are from RD1, RD2 to RDN, and all of these converters are connected to the DC bus using the cable resistance R line 1, R line 2, and so on and so forth. So now, since we know the prior estimates of cable resistance, and we also know the converter individual current information of the converters, with these known estimates of R line I for ith converter, I can estimate beta I, which is a product of the current contributed by that converter and the prior estimate of the cable resistance R line I. And we can use this as a feed forward control term in our system to achieve current sharing. Now, for this particular system, once I substitute beta I with the voltage drop across the cable resistance, I can solve the KVL equations and achieve current sharing between the two converters in just proportion to the loop resistance. So we go back to the ideal case where we achieve current sharing only in proportion to the loop resistance, and we overcome the limitation of the cable resistance. So for a radial system, I think it's easy to understand how we can eliminate the effect of cable resistance by using the prior estimates of cable resistance. But the question comes up, okay, what are the challenges with the multi-bus systems such as mesh configurations or ring configuration? So next, we will try to understand those challenges before going ahead. So to demonstrate the challenge, I'll take a simple example of a two-bus system. Here in this particular case, I have two converter 1 at bus 1 and converter 2 at bus 2. And they are connected at each of the bus. I have load, which I'm just for simplicity, I'm using a resistive load of R load 1 and R load 2 at bus 1 and bus 2 respectively. And these two buses are connected together by a cable tie line R12. Now, in this particular case, if I solve the KVL equation with conventional loop, I can show that the current sharing proportion between the two converters is in proportion not only of the group resistance, but it depends on R line 1, R line 2. It also depends on the tie and cable resistance R1, 2. And along with that, it also depends on the load distributions at the two buses, which are R load 1 and R load 2. So the challenge with the multi-bus system is that the current sharing accuracy does not only get affected by R line I, but it also gets affected by the cable resistance R line Rij, which are connecting the two buses. And this problem gets more complicated as we have more number of buses in the system. So the question that we try to answer in this research is that how do I compute beta I such that we eliminate the effect of R line I and Rij together to eliminate the effects of the voltage drop across the cable resistance, and we go back to an ideal current sharing scenario. On bus 2, we have a load at bus 1 and bus 2, which are being donated by R load 1 and R load 2. And these two buses are connected together by a tie and cable resistance of R12. Figure on the right also shows a bit more graphical representation. So I have node 1 and node 2, at which we have DER1 and DER2, which are connected to their respective nodes using cable resistance R line 1 and R line 2 respectively. And these two nodes are connected with the cable resistance R12, and we have a load at each of the bus. And this direct current sensor that I'm placing here is used to and we will just shortly find out that what is the significance of this direct current sensor. So the objective here is to eliminate the effect of the voltage drop across all three cable resistance, R line 1, R line 2, and R12. And beta 1 and beta 2 are the offsets that I'm generating for the two converters. So this is something which is important to understand at this point. And now if I solve the KVL equation for this particular system, I can show that the difference in the beta 1 and beta 2 should be equal to the voltage drop across all the cables that are present in the system, which are R line 1, R12, and R line 2. Now, how do we compute beta 1 and beta 2 is the next question. So to answer that, for simplicity, I'm separating voltage offsets into two components, the prime components and the double prime components. That is, beta 1 is equal to beta 1 prime and beta 1 double prime. Sorry. Similarly, beta 2 is equal to beta 2 prime and beta 2 double prime. Now, in order to eliminate effect of R line 1 and R line 2 first, what I'm saying that is that we know the local current information of the converters, which is IDC1 and IDC2 in this case. So beta 1 prime and beta 2 prime are used to eliminate the effect of the voltage drop across R line 1, as we did for the radial system. So beta 1 prime is given by the product of IDC1 and R line 1. And similarly, beta 2 prime is given by the product of IDC2 and R line 2. And now if I substitute these prime components, I can come up to an equation which shows that the double prime component, the difference in the double prime component should be such that it equals the voltage drop across the tie and cable, which is R12. Now, this is a single equation in two variables because we want to compute both beta 1 double prime and beta 2 double prime. So there are infinite solutions that could exist. But to come to a solution, the constraint that I'm trying to use is that we minimize the number of tie and current sensors that we use because we need to know the information of I12. And to achieve that, I'm placing a tie and current sensor closer to node 1 here, such that this information is locally available for the converters at node 1. And so the effect of R12, the voltage drop across R12, is being eliminated only by the converter sitting at node 1. So in that particular case, for this example, beta 1 double prime would be given equal to I12, which is being obtained using a tie and current sensor, and R12, which is basically the prior estimate of the cable resistance. And beta 2 double prime, I'll substitute with 0 because all the entire effect of the voltage drop across R12 is being taken care by the converter sitting at node 1. And now if I substitute all these variables and solve the KVL equation, I again go back to an ideal situation where I achieve current sharing between the converters only in proportion to the group resistance. So for the simple two-bus system, I can follow this particular strategy and achieve current sharing between the converters by using the prior estimates of all the cable resistances. Now let's look into little bit more complicated system. So in this particular case, now let's move to a three-bus system. In the three-bus system, I have three converters at one of each buses. So there are bus 1, bus 2, and bus 3. And similarly, following the same analogy of a two-bus system, I have a load at each of the buses, R load 1, R load 2, and R load 3. And these three buses are connected together with the tie and cable resistance R12, R13, and R23. Figure on the right again shows a similar graphical representation with the converter with the DER at each node 1, 2, 3, and load at each node. And these three nodes are connected together by the tie and cable resistances. Now, like what we followed for the two-bus system, I had separated the offset beta, which I want to obtain, into prime and double prime components. So similarly, I did for the three-bus system. And here the prime components, which again, I'm segregating such that the prime components will be used to eliminate the effect of R line 1, R line 2, and R line 3 in these figures. So which can be obtained by using the local current information of the each converter. So beta 1 prime and beta 2 prime and beta 3 prime are given here, which is nothing but the product of the local current information of each converter and the prior estimate of the cable resistance that we have. Now, like we did follow for the previous approach, I'm skipping the mathematical equations here in the interest of time. But what we want to do is we want to obtain the double prime component such that the effect of the voltage drop across tile and cable gets eliminated. And at the same time, I want to minimize the number of tile and current sensors that I'm additionally deploying in order to eliminate the effect of voltage drop across the cable resistance. So in this particular case, I'm putting a tile and current sensor on the tile line R12 and a tile line R23. And now I'm denoting this node 2 as the center node. So following the same principle as we did for a 2-bus system, the converters at node 2 do not act on the tile and current information, and they would be given by 0. But the converters at node 1 and node 3, will utilize this tile and current information and the prior estimates of cable resistance, and they are being substituted here such that the voltage drop across the tile and cables are being taken care by converters at node 1 and node 3. Now, again, if I solve the KVL equations, now since there are 3 converters in the system, I can show that after substituting prime and double prime beta components, I can achieve current sharing only in the proportion of the droop resistance between the converters. So for a 3-node system, we are able to solve this problem like we did for the 2-node system. But I think things get more interesting when we further expand the system. So now I'm going to a 4-node system, and the schematic of the system is shown here on the top left, with the converter at each node, load at each node, and all the nodes are connecting with the tile and cable resistance. So in this particular case, R12, R23, R34, and R14. And the figure on the right again shows us the graphical representation. So like we did for a 2 and 3 node system, the prime components can be easily obtained using local current information. So we are substituting beta 1 prime as IDC1 R line, IDCI R line I. But the things get more interesting when we want to eliminate the effect of all the tile and cable resistance, which are basically R12, R23, R34, and R14 in this case. Now, if I follow the same principle what I did for a 3-node system, I can again designate any of the node as the center node. So in this particular case, node 2 is the center node. So the double prime components of the converters and node 2 is being given by 0. And by placing the tile and current sensors on tile line R12 and R23, I can obtain beta 1 double prime as I12, R12, and beta 3 double prime again as the voltage drop across R23 using the tile and current information placed on R23. But if I do the same for the beta 4 double prime components, I can say that I will have to substitute beta 4 double prime either as this first equation or as the second equation. But by showing this additional marking, I'm trying to show that beta 4 double prime needs either the current information of the tile line sitting on R23 or the tile line current information of R12. So that means there has to be a communication between the nodes that would be needed if I want to utilize the method of using the prior estimates of cable resistance without using the communication within the nodes. So that would mean that beta 4 would need the communication of I23 or I12 in order to eliminate the effect of the voltage drop across the cable resistance. And so that is a limitation of the ring system that I tried to study here, that without the availability of communication network, ideal current sharing cannot be achieved among all the converters. It could be achieved only within the 3 converters, in this case, converter 1, converter 2, and converter 3. So this was something very interesting because we have been studying ring configuration for a long time, but from the power electronics point of view, in order to achieve current sharing between the converters, I think this was something interesting information that we learned during this research exercise. So the next question that naturally comes is, okay, then how can I eliminate this limitation and achieve current sharing among all the converters? So like initially we discussed that we have another configuration, which is the mesh configuration. So I try to utilize the mesh configuration if we could use that and achieve current sharing. So for this particular example, I connected the converters, the nodes 2 and 4 using a tie line, and placed an additional sensor on the tie line current on the tie line R24 or R42 in this particular case. The prime components are still given similarly as we did for the ring system, but in this particular case, the double prime components, beta 1 double prime, beta 2 double prime, and beta 3 double prime are still the same as we did for the ring configuration. But for the converter sitting at node 4, we can utilize now this current information and this tie line information and substitute beta 4 double primes, that is the product of I42 and R42, and we can show that if we substitute all these prime and double prime components, then we can achieve current sharing among all the converters. So basically, with this study, what we learned is that the ring configuration at 4 nodes has a limitation that we cannot achieve current sharing among all the converters, but the mesh configurations can help us to overcome that particular limitation. Naturally, I think the next question that comes up is that, okay, we have shown it for a 4-node system, then how do we construct mesh configuration for a generalized microgrid with n number of nodes? To do that, first I took an example of a 5-node system and I tried to construct the rules that have to be followed in order to form this system such that we achieve current sharing among all the nodes. So the first rule is that we assign any node as the center node, and the figure on the right shows us an example of a 5-node system. So node 1 can be assigned as the center node, and all the other nodes have to be physically connected to the center node. So we are connecting all the nodes 2, 3, 4, and 5 to the center node. And then we place tie line current sensors strategically on the nodes connecting the other node to the center node, which will be used by those converters sitting at each of those nodes in order to eliminate the effect of the tie line cable resistance. So this was an example of a 5-node system that if we follow these rules 1 to 3, then we can form this kind of system that help us to achieve current sharing among all the converters. But in order to mathematically frame this question, I use the concepts of graph theory in order to make sure that I consider all the possible configurations of the system that could exist. And one of the in graph theory actually is very pertinent to this particular exercise, which is called a k-apartheid graph. So I'll just briefly describe that graph and then show that how I use this particular graph in order to form these microgrid systems. So the k-apartheid graph can be described as a graph where all the nodes can be colored with the k colors such that the node to endpoints of an edge have the same color. So to show that, let's look at figure A on the left. So I am coloring these 5 nodes with 2 colors, green and the pink. And the principle of that graph is that the node to nodes of the same colors can be connected together. So here I could only connect node 1, 5, 1, 4, 1, 3, and 1, 2. And this is because I cannot connect node 2 and 3 as they are of the nodes of the same color. Then I can go to the figure B where I'm assigning another node to the green color instead of pink, which is node 2. And now I can connect node 1, 2, 3, 4, and 5, and similarly node 2 to 3, 4, and 5. But I cannot connect node 1 and 2 because they are of the same color. Third, I can assign another color here, which is orange, and assigning node 2 as the orange. Now I can still again connect node 1 and node 2 together. Now, this particular system, I can change the location of this third color or the number of times this third color appears such that I can form 3 different systems, which are being shown by C, D, and E, which could form the system where all the nodes are connected to the center node, node 1, and the other nodes are not connected to each other depending on what are the color of that particular node. So this basically is very pertinent to the system that I was trying to study, and I utilize these concepts to form a generic microgrid system. And following that, I can show that for a 5-node system, which I described using certain set of rules, that I can form 3 different configurations, configuration 1 to configuration 2 and configuration 3, which all will help us to achieve current sharing between the converters. And I'll just have to strategically place the current sensors on each of the nodes. So the concepts of graph theory help us to formulate these problems mathematically and also make sure that we don't miss any particular solution. Now, the same logic can be extended to a n-converter system. And in that particular case, I'm just showing that mathematically I can compute beta for all the converters. So, and then I'll just briefly show that how this method is being implemented in real time. So to show that, I'm just showing 2 particular converters which are at node K and node J, which are connected by the cable resistance R line IJ. And these 2 nodes are basically again connected by the tie line sensors. And since it's a group control strategy, first we have this voltage control, which generates the error between the reference voltage and the current voltage feedback. And at the same time, we have the group resistance. And this current reference is being compared with individual currents to pass through a current controller. And then we have PWM generator to control these converters. Now, the addition along with the group control is these feed-forward terms, which are being generated depending on the microgrid system that we have and the number of nodes in we have. So by using these feed-forward terms, we can eliminate the effect of cable resistance present in the system and achieve current sharing for a microgrid system with any number of nodes. To enable the controller design and analyze the stability, I also try to do some small signal modeling. And here, in the interest of time, I'll just show some results, but I don't expect to go a lot into the mathematical aspects of it. So I took an example of a two-bus system with a converter at each node and a load at each node. And I analyzed the small signal terms, the converter output voltage with respect to the reference voltage. So this is just a complete small signal model for this particular system where we have some cross-coupling terms between the converters since they are parallel together. And figure on the right just shows the validation of the small signal model with simulation results, using simulation results. And it shows that for different parameters, as an example, in the figure A, I'm varying the tile and cable resistance value. And the figure B, I'm looking at different types of load. Either it is only resistive load or there's a capacitance present along with the resistance. So for different types of load, the model works well. And the results show that the switching simulation model and the analytical model are in good agreement. So this model can be used in order to enable the controller design and analyze the stability of the system due to the presence of different cable resistances. We also try to validate this aspect in the lab. So I formed a small microgrid where I have multiple converters. So this is the rack where I'm placing 3 different converters. And these converters are connected with the tile and cable resistance, which are being shown over here with these resistors. And we have this bias power supply. And the converter topology that I used for this particular application was the dual active bridge converter topology. So we have the primary bridge and the secondary bridge. And these are the gate drivers for that particular converter. And then we formed the interface board, which hosted the controller card for this particular application. And these are some of the specs that we used to validate the concept in the lab. So I'll show 2 results in the interest of time. The first one is a 3-bus system where I have a converter at each node, and I'm placing 2 tile current sensors on tile R12 and tile R23. And the figure on the right shows the experimental results, where on the right side figure, on the top of this right side figure, I have the current of the 3 converters, IDC1, IDC2, and IDC3. And the bottom plot has the converter voltages from VDC1 to VDC3. Now, the way I'm trying to show the result is that till time instance T1, I'm running this strategy only in the conventional loop. So when I run only in the conventional loop, and the ideal current sharing between the converters selected for this particular case was in the ratio of 2:1. But due to the presence of the cable resistance and the conventional loop has this limitation, we don't achieve accurate current sharing, and the method leads to non-ideal current sharing between the converters. Now, at time instance T1, I activate the proposed control method. And after doing that, we can see that in the steady state, the contribution of each of the converter changes, and we go to ideal current sharing scenario in the ratio of 2:1. And to demonstrate that in the presence of dynamic load changes, I change the load at time instance T2, and then we again achieve the current sharing. So this this particular result shows that for a 3-bus system, we could achieve ideal current sharing among the converters due to the presence of by utilizing this particular method. Now, the another result that I'm showing is the 5-node system, which I tried to propose for this particular microgrid. And in this particular case, I'm assigning node 5 as the center node and strategically placing the current sensors. And also to show the generality of the system, I'm just having 3 converters here from node 1, node 2, and node 3. Node 4 and 5 do not have any converters, and node 4 just has a load. So we don't need to have a load and the converter at each of the nodes for this algorithm to work. It could be a sparse system where we don't have loads or the nodes at all the times at all the buses. And the figure on the right shows the experimental results. So again, like I did for the 3-bus system, till time instance T1, I'm running running my converter setup with only the conventional loop, which leads to the non-ideal current sharing between the converters. And then by activating the method, we see that the reference voltage of all the converters gets modified, and we move towards the ideal current sharing between the converters, which is in the ratio of 2:1. So these 2 results validate the concept in the lab for a 3-bus system and a 5-bus system, respectively. So this was the technical details of one of the control methodology that we have been working on, and I'll just present some summary results for the stuff that we have discussed. So in the initial part of the presentation, I tried to present an introduction and importance of the microgrid. Then we looked at some of the paralleling approaches that exist, which could be democratic current sharing, leader foreign current sharing, and the group control approach. Then we looked at an approach to achieve current sharing by using prior estimates of the cable resistance in detail. And we showed that for such system, the ring configuration has a limitation that we cannot achieve current sharing among all the converters once we have a 4-node or more than 4-node system. To overcome the limitation, we utilized the mesh configurations, and which are the new and the scalable configurations. They were inspired by k-partite graphs in the graph theory. And along with these, along with the configurations, we did try to propose a decentralized control method, which helped us to achieve current sharing among all the converters. So this was just a brief summary of the work that we discussed. And these are some of the references. And this is just an acknowledgement that I like to acknowledge my advisor, Dr. Subhashish Bhattacharya, for continuous support. And also, since it was an industry-sponsored project from Ford, I like to acknowledge the team from Ford Motor. Thank you.
So we have one question from Graham. He's curious if in your research you investigated the impact on differences in power capability of the DVRs on this control.
Right. So I think the question is that did I investigate the impact of different power ratings of the DERs?
Yeah.
Right. So yes. So when I go back to a result and try to show that. So in this particular case, I had 3 DERs in the top figure. If we look at a 3-bus system with a DER at each node, and these 3 DERs had different power ratings. So I had designed the droop resistance such that the power ratings of these converters was different in the ratio of 2:1. And that is what I'm trying to show, that with the conventional droop control, we don't achieve the power sharing in the ratio of 2:1, which is the rating of the converters. But with the method, we can achieve an ideal current sharing in the ratio of 2:1. So answer is yes. We did look at, I mean, it was a general methodology where we look into each converter could have a different power rating, and we try to achieve the current sharing in that rating.
So Dr. Lukic asked, in all cases, to solve for betas, you need all the information in a centralized solver. Is that right?
No process. So all the converters of each node need to know the information. There is no central controller. So it's a decentralized approach where converter, as an example, sitting at a kth bus would need the information of R line I, which is basically the resistance that is being connected, that converter to the node. And the other converters could need the tile and cable resistance. So there is no central controller. It's a decentralized approach where all converters need certain set of information. And the operation of the converters are also independent of each other. So there is no dependency between the converters when they operate.
Question. Then we'll go ahead and end this webinar. And this recording will be available, and so we'll send that out to the attendees. Russell, thank you very much.
Yeah, thanks, Ken. Thanks for the opportunity.
Appreciate it. Thank you, everyone, for joining. We'll stop the webinar now.
Thank you.